Hi everybody, today what we're going to do is we're going to talk about the basics of stoichiometry. Now, I'm going to tell you right now, this is my method of doing the stoichiometry. Some of you might hate it, and if you hate it, find another way of doing it. I really don't care how you do it. There are a semi-infinite number of ways of solving these problems. But the best that I can do is tell you how my brain works when I go to do one of these problems. And if you have a better way of doing it, by all means do it. You don't have to do it my way. But my way does have a very visual kind of organized aspect to what's going on. And again, if it's not doing anything for you, I can give you a different way to do it, or you can come up with your own way, or investigate a number of different ways online to do it. But this is what my brain does. So going further. Stoichiometry is a weird word. Its origins are stoichion from the Greek, which means element, and metry from the English, which means to measure. So what we are doing is we are measuring elements. So what we are going to try to do is we're going to try to figure out how much of one thing that we need in order to react with another thing. Now, before we get to the chemistry aspect of this, let's look at it in terms of cars and tires. Now, if I present you with one frame plus 4 tires goes together to make a car, nobody has a problem with that. And I'll bet you that I could give you any number of different ways to go about doing this, and you wouldn't have a problem with it. For example, if I were to tell you that instead of one car that was up on blocks and we were trying to figure out tires and so forth, if I had one frame that was up on blocks, instead of that, let's say that I had 5 frames instead. Well, it's not going to take a genius for us to figure out that you're going to need 20 tires to go on those 5 frames. Now, how did you figure that out so fast? Well, I need 4 tires for every 1 frame, right? So if you start here with the 5 and go over to the 20, then you're going to multiply that by a 4-to-1 ratio, 4 tires per 1 frame, right? And you're going to get to 20 tires. You barely even need to write it down. It's so obvious that's there. Or let's just say, instead of that, I tell you that you have 100 tires that are available, right? How many frames that are up on blocks could you fit with those with those 100 tires? Well, you would come over here, and you would know you would need 1 frame for every 4 tires, so you would be able to get 25 frames filled out with those 100 tires. So first of all, right off the bat, you notice that my method is examining these numbers that are here in our balanced equation, and we are going back and forth between these numbers, and we are always multiplying by where we are going and dividing by where we are coming from. So again, if I have 50 frames and I want to go over here to tires, I'm going to multiply by where I'm going, 4, divide by where I came from, 1, a 4-to-1 ratio, and I'm going to need 200 tires over here for that to work, because again, this number has to be bigger than this number over here, because I need 4 of these for every 1 of these over here, right? Now, we've completely ignored the cars, but the cars are pretty obvious at that point, because if I have 200 tires, then I'm going to go here by a 1-to-4 ratio, and yeah, I can make 50 cars. Or I could start here at 50 frames and go over here by a 1-to-1 ratio. Oh yeah, I'm going to make 1 car for every 1 frame that I have. So if you want to start putting things together to figure out how many of the other one you need, all you've got to do is be able to look at these mole ratios that are here from your balanced equation, right? Now, let me throw a curveball at you though. Let's just say, for the sake of argument, that I have 10,000 pounds of frames, okay? I've weighed them all out, and I have 10,000 pounds of frames. How many pounds of tires am I going to need in order to put on 10,000 pounds of frames? Now, your knee-jerk response was probably to say, I'm going to need 40,000 pounds there because it's a 1-to-4 ratio, and I'm going to go over here by 4-to-1. But think about that. Do you really need 40,000 pounds of tires to go on 10,000 pounds of frames? What piece are we missing here? Well, what we're missing here is that we are trying to compare the number of things with a real world unit like pounds, and it doesn't always work. In fact, it almost never works because tires and frames don't weigh the same. So what we really need to know is not how many pounds of frames that we have. What we really need to know is how many frames we have, or the number of pieces. So what do we need to know? We need to know how much a frame actually weighs. So let me tell you that, let's say a frame weighs 2,000 pounds. So if I have 10,000 pounds of frames and each frame weighs 2,000 pounds, you should be able to figure out pretty easily that that is 5 frames. Oh, okay. Well, that means I have 5 frames. Now I get it by a 4-to-1 ratio. I'm going to need 20 tires. But let me ask you this. Does a tire weigh 2,000 pounds? Not on any car that I've driven, right? Maybe Fred Flintstone's car back in the day, right? But probably not. Let's just say, for the sake of argument, that every tire weighs 50 pounds. Well, if I have 20 tires and I have 50 pounds for each tire, then 20 at 50 is going to get me 1,000 pounds of tires. So check it out. This real world example, I have 1 to 4, but I have not 4 times as many pounds of tires as I have frames, because frames and tires don't weigh the same. I have 4 times as many tires as I have frames, because I need 4 times as many tires, but not 4 times as many pounds of tires. So what we're going to see in all of these stoichiometry problems is that we are probably going to be presented up here with some manner of a real world unit. And by real world unit, I mean some unit that you can actually go in the laboratory and measure. Some real world thing. Maybe it's a mass. Maybe it's a volume. Maybe it is a molarity of a solution. It's going to be some real world tangible unit that you can measure in the laboratory. But there is almost nothing in the laboratory that tells you the important unit for chemistry, and the most important unit in chemistry is the mole. The mole tells us how many frames or how many tires there are, right? But there are no devices in the chemistry laboratory that tell you moles. There are scales that tell you grams. There are maybe solutions where you can figure out liters and so forth, but there are no measuring devices in the laboratory that tell you moles. But moles is what we need to use. So you have to be very aware that moles can be achieved in a variety of different ways. Maybe if I have a pure substance that's a solid or a liquid, I can just put it on the scale and get the grams of it. However, maybe it's a gas. We've learned all about gas laws. And so if it's a gas, I can use PV equals nRT because I can get the moles from N. Maybe it's a solution. And if it's a solution, then I need to know what the molarity is, the big M, because that's going to get me moles per liter. Maybe I can get moles that way. Or maybe I know what the number of atoms or molecules are, and I can take advantage of the fact that 1 mole is equal to 6.022 times 10 to the 23rd atoms or molecules that's there, right? So I can get moles in a variety of different ways. But that's like this. That's one step. That's going from a real world down here to our frames, because that's basically going to be our moles that's here. But once I get that, I have to move over by using our mole ratio and then back up by using another real world. So what we've really got is this guy here, which is a mole map. And odds are, guys, what's going to happen is that they're going to give you some real world unit, but they're going to want some real world unit over here. That's what's going to be given to you. This is what they're going to want over here. And if they give you a real world unit and they want a real world unit on the other side over here, then it's going to be probably a 3-step process. 1, where you turn it to moles. another where you turn it to the other moles, and then another where you come back out of that moles and figure out the grams or whatever of the other substance. So it's probably going to be where they give you one of these, they're going to expect one of these, so it's going to be 3 steps. 1 to get to moles, 1 to get to the other moles, and 1 to get to some other unit over here. So you have to be very fluid in how you interpret the information given to you, because you can get moles in a variety of different ways. And so what we're going to do now is we're going to walk through a series of different videos that are showing you how to kind of handle each one of these branches that are there and the different peculiarities that might arise when you do those particular problems. So let's start in this video, though, with the simple gram to mole to mole, and mole to gram kind of a situation, which is kind of what this car example is up here. I've given you mass, you figure out how many, you figure out how many of the other ones, and then you come back up to figure out the mass. Every one of these is going to be a 3-step process. So, what is it that we've got here? Well, what's going to happen is they're going to start you off with some real-world unit, and you're going to come down here with moles. So let's take a look at our balanced equation. It says how many grams of HCl? So this is going to want grams. They want that real-world unit. So again, when using this here, they want grams. But what did they give you? They gave you this guy here, and they gave you 200.2 grams of this. So they have given you grams of this. Notice on our equation, I cannot just go grams to grams. That is not allowed, right? So what I have to do first is I have to do grams to moles to figure out how many pieces are there. So how do I get from grams to moles? Well, my equation for molecular weight is grams per mole. So there's a variety of different ways that you can do that. Molecular weight is equal to the grams per the mole, or the grams are going to be equal to the molecular weight times the moles, or the moles are going to be equal to the grams divided by the molecular weight. All 3 of these are the exact same equation. You should be able to turn grams into moles or moles into grams very easily by using either of these equations. If you have the moles and you want the grams, you multiply by the molar weight off the periodic table. If you if you have the moles and you want the grams, you multiply by the molar weight. If you have the grams and you want the moles, you have to divide by the molar weight, right, like right here. So the first thing I'm going to do is I'm going to take these grams and I'm going to turn them into moles. Now I have to look up on the periodic table the molar mass of this. So calcium and carbon and oxygen, if I add all of that up, I get 100.1 grams per mole for his molar mass. So I've got grams, I want moles. So according to my equation, if I have grams and I need moles, I need to divide it by the molar weight, the molar mass. So 200.2 divided by 100.1 is going to get me 2 moles. Okay, great. Now I'm going to come over here to the HCl side. Now I'm going to use these numbers in front exactly the same way that I used those numbers for the tires and the frames. And the tires and the frames, it was 4 to 1. All I had to do to go from here to here was multiply by a 4 to 1 ratio. Now, my ratio is not 4 to 1 here, it's 2 to 1. But what I'm going to do is I'm going to multiply by where I'm going, 2, and divide by where I'm coming from, 1. Because again, guys, I am starting here, and I'm trying to get to over there. So I'm going to multiply by 2, that's where I'm going, and divide by where I came from, 1, and that's going to get me my mole ratio. So what that is going to come to down here is then I have 4 moles. Now what I have to do is I have to come back up to here, and I have to figure out the grams. So in my mole map, I have now done the following steps. I have now done that step, and now I have done that step, and now I got to come back out for this step over here. Now this is the same equation. Molecular weight is equal to grams per mole. But the first time I used it, it was for calcium carbonate. Now I'm going to be using it for HCl. They do not have the same mass. So I cannot use the 100.1 like I did before. I have to use hydrogen chloride's mass. And so if you look up hydrogen chloride on the periodic table, hydrogen is 1 and chlorine is 35.5. So that's going to get me 36.5 grams per mole. Now I know what you're saying. But Smith, there's a 2 there. Shouldn't I multiply that 36.5 times 2? No, you should not. Why? Because that 2 is already dealt with there in the same way that that 1 is already dealt with there. You already did that 2. That red 2 has already been taken into account in this problem, and so consequently, if you were to do it again, you would double count that 2, and therefore you would end up with the wrong answer. Like I said, there's lots of different ways to do these problems where you take the 2 into account for the math. I'm not going to do that. I am just going to take it into account with my mole ratio. So now what I've got is I have 4 moles at 36.5 grams per mole. So I get out my calculator. It turns out to be about 146 grams. I need about 146 grams to do this one. So you'll notice it's a 3-step process. Go from the real world unit, grams, to moles. Go from the moles to the moles of something else. And then come back out using the real world thing of grams again. Let's try it again. This guy here says how many grams of oxygen are necessary to completely react with 64.1 grams of sulfur dioxide. Fine. So I have a real world unit here. I have 64.1 grams of this, and I want grams of this. So I go up to my mole map, and I realize that I have grams of sulfur dioxide, and I want to end up with grams of oxygen over here. And so I can't do that in one step. Those circles are not connected. I have to do it in 3 steps. Step 1, go to moles. Step 2, go to moles. Step 3, come up to grams. So step 1, I have to turn this guy into moles down here. So I look up the mass on the periodic table, and it turns out that sulfur dioxide has a mass of 64.1 grams per mole. Now you might say to yourself, but Smith, there's really 2 that are there, so shouldn't I multiply that guy by 2? And the answer is no. I mean, you can. That's one way of doing it, but I highly recommend that you don't do it that way. We'll take that 2 into account, I promise. We're just not going to do it right now. So I've got this formula, which is right here, the SO2. That weighs the 64.1. So it turns out I have 1 mole, right? Now I've got to move over here to my oxygen. Now I'm going to take that into account because I've got a 2 that I'm starting with, but I'm going to be half as much over here in the oxygen because I only have 1. So I'm going to multiply by where I'm going, 1, divide by where I'm coming from, 2. So I'm going to end up with 0.5 moles of oxygen. Now I got to come back out by using just the mass of oxygen. So just the mass of oxygen is O2. That's 32 grams per mole. At half a mole is going to get me 16 grams. That's there. So in each of these cases, you start with the grams, you go to the moles, you go to the moles of the other thing, and then you come back out. It's a 3-step process. Let's try another one. How many grams of iron can be produced from 428 grams of Fe2O3? Okay? So that's the real world unit. Now I got to get to my mole world. So first thing I do is I'm going to add up the mass for this guy. So that's 55, 85 twice, and 16 3 times is 48. That's going to get me a mass of about 159.7 grams per mole. So that guy weighs about 159.7 grams for a mole. So I take my 428 and I divide it by 159.7, And that's going to get me about 2.68 moles here to 3 significant figures. Now I'm going to go from there over to here because that's what I want. What's my mole ratio? It is a 2 to 1. So the 2.68, I'm going to multiply by 2 and I'm going to divide by 1 because you always multiply by where you're going, divide by where you came from. So it's a 2 to 1 ratio. So that's going to be a 5.36 moles that I have here. And now I'm going to come back up to my real world unit because I want grams, and I just have to use the molar mass of iron. And that molar mass is 55.85 grams per mole. But Smith, there's a 2 there. Shouldn't I multiply it by 2? No, because you already did. You already took that 2 into account when you did it down here. So you don't have to double count that 2. So it's 536 at 55.85 gets me right at 300 grams, 299 grams is the answer there. One more. How many grams of iron can be produced from 125 grams of aluminum, assuming that we have all the other stuff there? All right, first thing I'm going to do is take my real world unit and turn it into my mole world unit. Aluminum weighs 27 grams per mole on the periodic table, because again, that's its formula. But Smith, shouldn't I multiply it by 2 here because there's a 2 in front? No, that 2 you're going to deal with when we go to this step here, when we deal with the numbers that are in front. So don't take that 2 into account now, just do the formula. So that's 125 divided by 27 is going to get me a number of about 4.63 moles that are there. Now I'm going to deal with that 2. Why? Because I'm going to go across town, and I'm going to go across town by a 3 to 2 ratio, so I have to multiply it by 3 and divide it by 2 because you always multiply by where you're going and divide by where you came from. So times 3 halves is going to get me about 6.94 moles there. And now I'm going to come back up out of the mole world into the real world, knowing that iron is 55.85 grams per mole. So 55.85 at 694 is going to get me about 388 grams that are right here. But Smith, shouldn't I do 3 times the fit? No, you've already done the 3. You've already done the 3. That 3 was taken into account at that step in the same way that 2 was taken into account on that step. So those are some basic stoichiometry type problems for